Given a closed boundary and closing a surface, we want to find the minimal surface. This is an interesting problem. For example, if we are in two dimensions and we have a closed boundary, well, the obvious solution, the somewhat obvious solution would be that this area here inside this sort of rectangle is the area which minimizes this surface. So it's the minimal surface. Anyway, it's more complicated if we reason in three dimensions. So we might have curves which stick out from a plane, and therefore we are reasoning in three dimensions. And we will seek the solution in a form that we have a function of the kind z equal to z of x and y. So it is a function of two variables which can be written explicitly like this. So this is an explicit function because z, which is the variable that we have on the z-axis indeed, is of the form z equal to z of x and y. So this is the form of the surface. Now, in general, if we have a certain displacement vector r, we can write it in the form x, y, z, and z is a function of x and y. So r starts from the origin and then it points towards a point which belongs to the surface. And by means of this vector, we can describe any kind of surface of this form. Now, according to multivariable calculus, if we want to find the area of a surface, well, we need to parameterize the surface by using two parameters to describe the surface. And in this case, we will use the two parameters x and y. So we need two parameters because we can describe the surface as a function of x and y. In other cases, we might have some other parameters like u and v that might not necessarily be equal to x and y. Once you study multivariable calculus, you realize that if you take the determinant of a certain matrix, which is given by, in particular, the cross product between dr dx and dr dy, so you can write this cross product by means of a determinant. You have the three unit vectors I, j, and k in the first row. Then in the second row, you have this derivative. So the derivative of the first component of r, which is x, with respect to x is equal to 1. Then here you have 0, and then here you have z sub x. So it's the partial derivative of z with respect to x. And here you have 0, 1, and z sub y. So this 1 comes from taking the derivative of the second component of r, which is equal to y, with respect to y. So you take this determinant, and then if you want the area, you really have to consider the magnitude of that quantity. And once you do the calculation, you get something quite simple. So the magnitude of the resulting vector from here would be the square root of the sum of the squares of the components. And what you get is 1 plus z sub x squared plus z sub y squared. This is what you get. So you can write down a double integral of the following kind. So you have a function a, and you have a double integral over a certain contour. So you integrate over a surface, but the surface is delimited by a contour. So we keep the contour fixed, and then we will take the variation of this area. So that's how we minimize the area given a certain contour. So here we have the square root of 1 plus z sub x squared plus z sub y squared, and then here you have the differentials dx and then dy, like this. Once you take the variation, of course, you will have, what do we have? We have the Lagrange equations. So here we call this f, and this f is a functional because it depends on another function which is z, and also its derivative. So this would be a functional that depends on z, z sub x, z sub y, and in general it might depend on x and y as well. So the Lagrange equations in this case would be the partial derivative of f with respect to z minus partial derivative with respect to x of the derivative of f with respect to z sub x minus derivative with respect to y of the derivative of f with respect to z sub y. And then you set it equal to 0, like this. Now you can see that the partial derivative of f with respect to z is equal to 0 because f does not depend explicitly on z, it depends on the derivatives, these derivatives here. And the derivative of f with respect to z sub x can be easily calculated to be z sub x divided by square root of 1 plus z sub x squared plus z sub y squared. And similarly, here, this derivative would be z sub y divided by the square root of 1 plus z sub x squared plus z sub y squared, like this. And finally, we get to the equation of minimal surfaces, which can be written in the following fashion. So you have derivative with respect to x. Here you have z sub x divided by the square root of 1 plus z sub x squared plus z sub y squared plus derivative with respect to y of z sub y divided by the square root of 1 plus z sub x squared plus z sub y squared, and then this will be set equal to 0. Now, it's quite easy to realize that there is one trivial solution of this difficult equation. This is quite complicated, as you can see, because it has derivatives with respect to x of the function z, and it also contains derivatives of z with respect to y. So it's a mixed kind of equation, and it's complicated. But of course, for example, if z is equal to a constant, well, the solution is trivial. You get 0 equal to 0 there. So this solution, so this equation, z equal to a constant, is a solution to the equation above. And of course, this describes a plane, and this is expected. This is to be expected. But the question is, are there other solutions to these complicated equations which are non-trivial? The answer is that there are such solutions, such non-trivial solutions. And in particular, two non-trivial solutions are known. And we will show that, I mean, we will not do all the steps because this is just algebra after all, but we will show that there are other solutions. And one solution is the so-called catenoid. And the other solution is the so-called helicoid. So the catenoid is a surface of revolution which is generated by rotating a catenary curve about an axis. So what is the catenary? The catenary, if we have a function of y of x, for example, so we assume that we are in two dimensions, we have y of x, which is a function of x in the following fashion, so in the following form. We have a constant a, and then we have the hyperbolic cosine, cosh, of x divided by a. So a is just a constant, the variable here is x, and this is just a curve that you might have studied in multivariable calculus or in single variable calculus as well. I will not describe this curve, but then if you rotate it around a certain axis in a certain fashion, you will obtain a function of the following kind. You have z, so in this case we write down the function of two variables z of the square root of x squared plus y squared, which we can simply call r. And then here we have a cosh of r divided by a. So by rotating this curve appropriately around a certain axis, we get a function of this form. Now, once you know how to compute derivatives, it is quite straightforward to take this function, and remember that r is a function of x and y just like this. It is trivial to put it inside this equation, to substitute it there, and show that indeed the equation is satisfied. There are some symmetries which might simplify the calculations. I mean, they are really straightforward calculations, and what you get is that indeed this function solves the equation above. Another equation, as I said, is that of the helicoid. The helicoid is a helical surface. It is the surface traced by an infinite line that is simultaneously being rotated and lifted along its fixed axis of rotation. If you consider cylindrical coordinates r, theta, and z, you have a function written like this: z equal to a constant multiplying the angle theta. So this is considered to be a helical surface. And if you go back to the coordinates x, y, and z, the angle theta can be written as the arctangent of y over x. So basically, y is equal to the tangent of theta times x. So in the xy plane, x, y, and z, so you have a point on this plane. The angle theta is measured like this, and this point has a coordinate equal to x and the other one equal to y. You can see that the relation between x and y is indeed this one. So y is equal to the tangent of theta times x. And now you can take this as the definition of our helicoid, z equal to c arctangent of y over x. And indeed, also in this case, if you substitute the expression in here, what you get is indeed that the equation is satisfied also for the helicoid. So the helicoid and the catenoid are two non-trivial surfaces that solve the minimal surface problem.